Okay, good morning everyone. My name is Reeme and Jeffrey, and together with my partner Asrul, we will presenting our assignment for ETS551, Digital Signal Processing. Our presentation today focus on digital filter design, where we will take you through the specific engineering trade-off between ideal mathematic model and physical reality of practical hardware implementation. First, what is digital filter design? A digital filter is a mathematical algorithm or system that processes a discrete time signal to change its frequency characteristic, allowing wanted frequencies to pass through while blocking or reducing unwanted noise. There's two types of digital filter design, which is FIR, finite impulse response filter, and IIR, infinite impulse response filter. Okay, here first the for assessment one, which is I will be presenting. For question one, using the given specification, sketch the ideal and actual FIR low pass filter magnitude response, clearly indicating the pass band, stop band, and transition region, pass band as frequency, attenuation, and stop band, and expected ripple behavior. As you can see from this sketch, the magnitude response of both ideal and a practical in FIR response low pass filter to visualize our design parameter. The blue dash line represent this blue line. This represent the ideal theoretical brick wall filter, which feature a perfectly flat passband and instantaneous drop zero at the cutoff. This part. However, because the physical system cannot achieve the finite number of coefficients, the red line illustrates the actual realizable filter response, which is from this until down this. For the ideal filter, which is from pi to omega pi, rest up until 1, and then drop back from omega c to positive pi. So next, let's move to question 2. For the question 2, using the Henning window method, which is omega n is 0.5 minus 0.5 cos 2 pi n over n. The first thing, we need to find the delta f, which is c over n. I mean, we need to find the number of n, which is delta f equal to c over n, where 0.1 equal to 3.1 over n, which is n equal to 31. So we input into the original equation, which is HDN for low pass filter is 2fc sine omega c n minus alpha over omega c n minus alpha. For this, I'm looking for the value of alpha, which is alpha equal to n over 2 equal to 15.5. And then I look for the value of fc. fc equal to fpn plus fsn over 2, which is 0.2 plus 0.3 over 2, where I get the fc equal to 0.25. Then I'm calculated the value of omega c. Omega c is 0.5 radian per second. Therefore, HDN equal to 0.5 sine 0.55 in bracket n minus 15.5 over 0.5 pi in bracket n minus 15.5, where Hn is HDN multiplied by omega n. So I get this last formula for n equal to 0 until 31 for this equation. Next is question for 1 Roman 3, FIR for n if n equal to 32 until n equal to 34. For HD, n equal to 32, I'm putting the 32 into the n formula, the equation that I get from the Roman 2. which I get the HD for 32 is 0.065, negative 0.0065. And for HD for 33, I get negative 0.0054. And for HD for n equal to 34, I get a positive 0.0039. So increasing the filter order n will be add more coefficient to the equation. This forces the device embedded microcontroller to compute more mathematical operation for every single sample. So this is for assessment 1. So I'm passing this to my partner Asrul for assessment 2.
Assalamualaikum, my name is Asrul bin Papes alias Kamarudin, and I'm going to continue the solution for assessment number 2. And before I start it, I'm going to show you the equations that I'm going to use. First is these three equations that I'm going to use for my solutions, and the equation for the first Roman is determine the selectivity factor K, discrimination factor D, and filter order. So as you can see, for selectivity factor K is equals to omega P over omega S, and from the questions we know that omega P is equals to 0.3 pi and omega S is equal to 0.5 pi. So we're going to input the value into the equations, into the formula, and we got K is equals to 0.6. And the next one is discrimination factor D. Since we don't have the value of delta P and delta S, we're going to use the next formula, which is square root of 10 Rp over 10 minus 1 and over 10 As over 10 minus 1. We're going to use this. And since Rp from the equation is 27 and As equals to 40, we're going to input the value into the formula, and we got 0.2236. And for the filter order, the formula that I'm going to use is n more than equals to log 10d over log 10k. We got the value of d and k from the equations earlier, which is d equals to 0.2236 and k equals to 0.6. We put the value in the calculator and we got 2.93. We're going to sum up into 3, so n equals to more than 3. For the second Roman questions, determine the 3 dB cutoff frequency omega c to any value within the range. We're going to use the equations, this one, since we don't know the value of delta P. We're going to use this one. So omega c more than equals to omega P bracket 10 to the power of Rp over 10 minus 1 to the power of negative 1 over 2n. And we got 3, and Rp we got 27. So for these equations, omega P also was given from the questions, which is 0.3 pi. So we calculate the value for the bracket first. We got 0.3549 and times with 0.35, we got omega c equals to more than 0.3345. And the last question is determine the system function based on calculated left hand side LHS poles. Then evaluate the IR IIR low-pass filter by using the design formulas based on digital backward filter specification. Validate your design using MATLAB. So we're going to design the system first. Firstly, we're going to determine the left-hand side poles. We n equals to 0, 1, and 2 because n minus 1 equals to n minus 1 equals to 3, so n is 0, 1, 2. Oh, for this formula, I'm going to use Pn, which is n, the number of 0, 1, and 2, and omega c times with exponent j n plus 1 plus 2n times with pi over 2n. This one is possibly, this one is 3 and this one is 3, and this one is 0, 1, and 2. Omega c, we got 0.3345. So for PO, for PO is 0. By using this equation, this formula, PO, this one is 0, and this one is 3, and this one is 3. So sum it up, we got 2 over 3 pi. So we're gonna use when we're going to use where exponents j with any value, we transform it into cos a plus j sin a, cos a plus j sin a. This one will be into this one. So we calculate the cos 2 over 3 pi and sine 2 over 3 pi. For cos 2 over 3 pi, we got negative 1 over 2, and sine 2 over 3 pi, 0.8660. We're going to multiply with 0.3345, which is the omega c, and for poles for PO, we got this one. And for P1, we only need to change the number, the n, small n, for this one, and change it into 1. So we got 6 over 6 pi. We can simplify to only pi and do the same as the PO. Cos pi, we got negative 1, and sine pi, we got 0. So for this poles, we only need to multiply with negative 1. So we got negative 0.3345. And the last n, the last small n, I change the n with 2 and n with 3. So we got 8 over 6 can simplify with 4 over 3. Do the same as before. Cos 4 over 3, we got negative 1 over 2. And sine 4 over 3, we got 0.8660. Multiply with 0.3345, our omega c, and we got this as the value. And the last one, we need to synthesize the system where HAS equals to, this one is omega c to the power of 3 or cube, and S plus, S negative PO, S negative P1, and S negative P2. P2. So the value negative will be times with negative, it will become positive, and positive times with negative become negative. So this is the final answer for questions number 3, and we're going to validate the questions using MATLAB. So this is the MATLAB coding. For the K, D, and N, we're going to type the coding same as the formula that we use. And this one is for the it's the command that we use to to know the output. And the command window is this one. This is the poles, and this is the transfer function. And the figure that we will get is this one. This is for magnitude, and this is for phase. So for the magnitude, it will become like this because because the n is increasing from 0 to 1 to 2. This is the characteristic of IIR Butterworth low pass filter response, because as the frequency is increasing, the magnitude is decreasing. And for the phase, as the frequency is increasing, the lagging phase for this will be dramatically decreasing. It become negative. So that's all from me. Thank you.